Good evening. Today we are going to solve some sample problem regarding week 11. So I'll start. So this is week 11 and myself Shubham and the course TA which is this thermodynamic classical to statistical taught by Professor Sandeep Paul. So first of all we will start solving some we will solve some questions that are given in assignment, and so before that we will solve these formula and all. So we will revise initially and then we will go to the question part. So I'll start with this heat capacity of monatomic crystals. So we know that there are two theory which explain this. One is Einstein theory of heat capacity. Einstein theory of heat capacity, and other is Debye theory of heat capacity. So I will not solve the expressions, just give you the idea and the results which we get from these two theories. So first, the Einstein theory. So first of all, what does it assumes? Like assumptions. First assumption is that they consider it as ideal crystal. That means there are n non-interacting particles. So there are n non-interacting particles in the, that is particle is atom basically. So in this system, this is the n non-interacting atoms. So this is ideal crystal, which means, like, let's say this is the crystal for, let's say, something called magnesium, let's say. So all these are the magnesium atoms, but they are not interacting with each other. There is not any kind of force between them. They are independent of each other. So then this is called ideal crystal. Number two, second assumption is that each particle have its own vibration, which means that vibration of each particle is independent of other particles. So if this is vibrating, it is vibrating independently. It is not dependent on the other atoms. So then how many degree of freedom will the system have? Like if one particle is vibrating independently, it can vibrate in 3 directions. So it will have 3 degrees of freedom. So let's say there are n number of particles in the system, then there are 3n degree of freedom for vibrations. So there are totally 3n degree of freedom for the vibrations. This is according to Einstein theory, all these assumptions. So next, third one is that there are not any electronic rotation or translation motion. So third point is there are not any electronic rotation or translation modes of motion in the monoatomic crystal. So this is the third assumption. So if we write the partition function, that will be the vibration partition function only. And since there are 3n degree of freedom, so we can write it as q vibration to the power 3n. So this is the q vibration. So we can solve this and get the value of this heat capacity. From this we can calculate ln q vibration, and from after calculating ln q vibration, we can use that formula u is equals to nkb t square curl by curl t of ln q vibrational at constant volume, then differentiating u with respect to temperature at constant volume is Cv. So this is how we can calculate the q vibrational. Okay, so we have the equations. If we solve these, like we can take logarithm of L, if we take logarithm of q vibration to the power 3n, that will come 3n ln q vibrational, and we know that q vibrational is nothing but e to the power minus theta by 2t divided by 1 minus e to the power minus theta by t, and we know theta is equal to h nu by kb. So these are the equations what we are getting here. So ln q vibration is equal to 3n ln of e to the power minus theta by 2t divided by 1 minus e to the power minus theta by t. So taking the log differently, then ln q vibration is equal to 3n, that is minus theta by 2t minus ln 1 minus e to the power minus theta ln 1 minus e to the power minus theta by t. So by solving this, we will get the value of ln q vibrational, and by putting the value in the formula of u, we can get the value of u, and from u we can calculate Cv. So after solving these equations, I am not solving the equation because these are already solved in the class, so I'll just write the answer now. So according to Einstein theory, at temperature T tends to 0, Cv also tends to 0, and at temperature T tends to infinite, Cv is nearly equals to 3R. Okay, so this is the formula that we are going to use. So what is the limitation of this assumptions? Limitations. So the main limitation is that it cannot give the correct value of Cv in the lower temperature range and intermediate temperature range. So it is only good for the temperature which is very high. For the moderate temperature or lower temperature, it does not give any correct value. So it is not successful for the temperature, low temperature and very high temperature. So then there is other theory, that is Debye theory, so which is quite successful as in giving at any range of temperature, giving the value of Cv. So Debye theory. According to Debye theory, Cv is equals to A T to the power 3. I just write the formula where A is the value of A is 12 pi 4 I R by 5 theta D to the power 3, and theta D is characteristic Debye temperature. Characteristic Debye temperature. So this is for crystal monatomic. So we can say that according to Einstein it is 3 R. Okay, and for Debye it is A T to the power 3. Now we will solve some problem based on now this is the entropy and the enthalpy. We will solve some problems on entropy, enthalpy, internal energy, and this adiabatic and isothermal expansion of gas, and heat capacity. A few questions on this partition function. So we will just quickly go through the formulas of this enthalpy, entropy, internal energy and at all. So first of all, we know that first, according to first law of thermodynamics, du is equal to dq plus dw. Okay, and we also know that dh is equal to du. Okay, that formula, delta h is equal to delta u plus delta ng RT. So this formula we are going to use. Delta ng is the number of change. This is change in number of moles of gas in the reaction. So this enthalpy of the reaction we can calculate if internal energy is given and the reaction is given. So this is we are going to apply. Okay, and then this entropy, formulas for entropy. Okay, so entropy for reversible process and ideal gas. So we have a few formulas. First, when temperature and pressure are given, so then delta S is equals to, we will apply this formula, then NCP ln T2 by T1 minus N R ln P2 by P1. So this is applied when the temperature and pressure are given. Second one, when temperature and volume are given. So delta S is equal to NCV ln T2 by T1 minus NR ln plus NR ln V2 by V1. Okay. If the process is isothermal, what if the process is isothermal? Then this part and this part will be 0 for isothermal process. So delta S will be minus NR ln P2 by P1, that is equal to NR ln P1 by P2, and from this formula it is NR ln V2 by V1. So either of these formula can be used. Now we know that for solid and liquids, change in volume with temperature is 0. So for solid and liquid we can say that V2 by V1 is equals to 1 and ln 1 is equals to 0. So this part will become 0 when for liquid and solid. Now for this phase transition, so delta S is equals to delta H of transition divided by temperature of transition. This is another formula of entropy. So this formula we are going to work with. Now next, okay, that we are talking about this isothermal and adiabatic reversible processes. So we know that for isothermal reversible process, PV is equals to constant. That means P1 V1 is equals to P2 V2 at constant. Obviously this is at constant. Okay, this is isothermal process, so temperature is constant and gas is ideal gas. Ideal gas and isothermal process, PV is constant, that is P1 V1 is equal to P2 V2. And for adiabatic reversible process, for ideal gas, PV to the power gamma is equals to constant. Okay, there are other formula like T V to the power gamma minus 1 is constant. So these two formulas apply well for the adiabatic reversible process, where gamma is equals to Cp by Cv, heat capacity at constant pressure divided by heat capacity at constant volume. So this is the adiabatic reversible and isothermal reversible processes. Now apart from this, we are going to use these partition functions as well. So the main is vibrational partition function. So we know that for, if we consider E naught is equal to half h nu, this is exact ground state energy. So if we consider for system, if we are considering E naught is equal to half h nu, then Q vibrational partition function is equals to e to the power minus theta by 2t divided by 1 minus e to the power theta by t, where theta is equal to h nu by kb. Okay, and for if we consider E naught is equals to 0, then Q vibrational will become 1 over 1 minus e to the power minus theta by t, where theta is equals to h nu by kb. So if we consider 0 point energy at 0, then this formula will apply, and otherwise this formula will apply. Okay, so this is also we are going to use in a question. So I am just revising the formula that we have studied this in previous classes, but I am just reminding them before solving the question. Now this Q translational partition function is 2 pi m kbt divided by h square to the power 3 by 2 into volume. We can write it as V by lambda Q. So what will be the lambda then? Lambda is equals to h upon, this is cube, so under root of 2 pi m kb t. This is lambda. Lambda is de Broglie. Well, okay, now this rotational partition function, so QROT, this is equals to KBT by sigma HCB, where B is equals to H upon 8 pi square IC. Okay, where sigma is symmetry factor. Sigma is equal to 2 for this diatomic gases, homo nuclear diatomic gases like H2, Cl2, etc. Whereas sigma is equal to 1 for heteronuclear, like some other gases like this carbon nitride gas and so others as well. Okay, so now we will move to the questions. And I will solve the assignment question first. Okay, this is the question number 1. This is from the assignment only. The value of molar heat capacity at constant volume will be, okay, that we have just done this according to the Einstein formula. Like, since there is no temperature is given, so we will apply this Einstein formula, where CV is approximately equal to 3R. So we need to calculate it in calorie per mole per degree per unit. So CV is equal to 3 into 2, that is equal to 6 calorie. This, since R is in calorie per mole per Kelvin, so this is the answer, 6. So this 6 is the answer. If that temperature is, if they have given temperature, then we can apply that Debye theory. So since there is no temperature, so we can easily calculate it by 3R formula. CV is equal to 3R, Einstein formula. Now question number 2. Molar volume of metallic magnesium is given 26.1 centimeter cube. Each atom of magnesium contributes its 2 3s electron to the conduction of electron gas. Okay, determine the Fermi energy. Formula is given. So the formula is given, and they are asking for this EF, and they are saying that there are 2 3s electron that is contributing to this Fermi gas. So each magnesium is contributing 2 electrons. So that means if there are n number of, then there if we are solving for 1 mole, so then there are 2 into Na electron in the Fermi gas. So formula for EF is given. EF is equal to 3 n divided by 8 pi v 2 to the power 2 by 3 into h square by 2m, and all the constants are given. You just need to put the value and get the answer. So what else is given? This volume V is equal to 26.1 centimeter cube, and since all the units are in their standard, so I'll convert this into standard as well. So this will be meter cube in SI. So 1 centimeter is 10 like 10 to the power minus 2 meter. So it is to the power 3, so it will be 10 to the power minus 6 meter cube. 26.1 into 10 to the power minus 6 meter cube. Okay, and n are the number of Fermi particle. So this will be 2 into, for 1 mole of magnesium, it will be 2 into Na. Na is Avogadro number, that is 6.023 into 10 to the power 23. So this is given. No, this is not given. So this is okay, this is given. So n is 2 into this. Then now we can put the values and get the answer. 3 into 2 into 6.023 into 10 to the power 23 divided by 8, pi is 3.14, volume is given 26 centimeter cube, that is 26.1 into 10 to the power minus 6 meter cube. So since all the units are balanced, so I am not writing the units because I am using SI only. So H is 6.626 into 10 to the power minus 34, and H square we are taken. So H square divided by 2, and mass of the electron is 9.1 into 10 to the power minus 31. Okay, just solve this by using calculator. Three into 2 into 6.023 is 36.132 into 10 to the power 23, and the denominator it is 8 into 3.14 into 26.1. This is 655.632 into 10 to the power minus 6. This side, this is 6.626 square, that is 43.9 into 10 to the power minus 68 divided by 9.1 into 2, that is 18.2 into 10 to the power minus 31. So now this is if we take this 3613.2 into 10 to the power minus 21, then this will be 36.132 into 100 divided by 655.632. So this is 5.51. Okay, 2 by 3 here. 1 into 10 to the power 21 plus 6, 27 to the power 2 by 3, and this side it is 3.9 divided by 18.2. This is 2.4 into minus 68 plus 31 minus 68 plus 31, it is 10 to the power minus 37. So we can solve this. Okay, I'll erase some part, make the space here. Okay, now we need to just solve this power first and then multiply this. So this power we are solving 5.5 to the power 2 by 3, 5.5 square and then cube root. This is 3.11. So this is 3.11 into this 10 to the power 27 into 2 by 3. This is 9 into 2, 10 to the power 18 into 2.4 into 10 to the power minus 37. So into 2.4, this is 7.478 into this 37 minus 18, 10 to the power minus 19. So this is the answer, and the unit we know the is joule, since we are taking SI unit, so it is joule. So answer D is correct, 7.53 into 10 to the power minus 19 joule. Now the third question. Two particles have to be distributed in 3 energy levels. So number of particles are 2 and number of states are 3. The ratio of probability that the two particles occupy same state to the probability that two particles occupy different state for Boltzmann-Einstein statistic is. So we know the how many microstates there can be. So since we know that for Bose-Einstein statistic, number of microstate W is equals to n plus m minus 1 factorial, where n is the number of particle, m is the number of states, divided by n factorial m minus 1 factorial. So this formula is for total number of microstates. So if we calculate by using this, 2 plus 3 minus 1 factorial divided by 2 factorial, 3 minus 1, 2 factorial, that is. So this is 3 into 5 minus 1, 4 factorial, 2 factorial, 2 factorial, 2, 4 into 3 divided by 2, this is 6. So there are 6 number of microstates. Now they are saying that in 3 state, if case 1, if the particles are distributed in 3, the ratio probability that two particles occupy same state. So if both the particles are occupying same state, then there are only 3 possibilities. Either they are in first this state or this or that. So there are 3 possibilities of both the particle in same state. Then the probability will be 3 by 6, that is 1 by 2. Okay. Probability of having two particles in one state will be 1 by 2. Now two particles occupying different states. If they are in different states, so they can be in this, like this, in first or second state, or they can be in first or third, and they can be in second and third. So these are 3 combinations only. So probability will be 3 by 6, again 1 by 2. So this is the probability of first, and this is the probability of first condition, that is to both the particles in same state, and this is for the both the particle in different states. So both are half. If we take the ratio, the ratio probability we need to calculate, then ratio P1 by P2 is equal to half divided by half, that is equals to 1. So the probability of ratio probabilities will be 1. Easy question. So now to the question number 4. Identify particle. 5 identifiable particles are distributed in 3 non-degenerate levels with energy 0, E and 2E. Okay, there are 3 energy levels with energy 0, E and 2E. The most probable distribution for the total energy 3E is. Okay, first we just simply write all the combination with energy 3E. Let's say there are 5 particles. So let's say there are 3 particles in ground state 0 and 1 in E first and 2 in 2E. Then this will be, okay, this will exceed, sorry, total energy should be 3. So 1 in 2E, 1 in E, and rest 3 are in 0. One possibility. Other possibility is 2 to 4, 2 and 3 energy. Okay. 1 in 2E. Okay, no. Next is 3 in E and 2 in 0. Any other possibility? This will give 3 only. So next is so I don't think there are any other combination. There are these 2 combinations only, and out of these they are asking the most probable distribution for total energy 3E is. So it is quite clear that we know that the most number of particles lies in ground state. So the most number of particles should lie in ground state. This distribution should have the most probable distribution. So this distribution is N1 have 3, N2 have 1 and N3 have 1 particle. So 3, 1, 1, this is the answer. The next question. Temperature. The temperature of 72 gram of water is raised from 30 degrees Celsius to 80 degrees Celsius at constant pressure. Change in enthalpy of the system is. So need to calculate change in enthalpy. Change in enthalpy of the system, and delta T is given, that is 80 minus 30, that is 50 degrees. So delta T is given, mass is given 72 gram. Water is the system, and we know that Cp is curl H by curl T at constant volume. So we can say Cp dt is dH, integrating from T1 to T2 and H1 to H2. This will give Cp T2 minus T1, that is equals to H2 minus H1. This implies delta H is equals to Cp delta T. Okay. So Cp is given, molar Cp is given. So Cp molar is given. So let's say this will become, then if Cpm is given, that will be n Cpm delta T for n number of moles Cpm. So delta H is equal to n Cpm delta T. This is for Cp for n moles, and this is for 1 mole. So for n mole, Cp is equal to n Cpm. So I just put it the value here. Okay, so delta H is equal to n Cpm delta T. All the values are given, so we can calculate it. Delta H is equal to, okay, number of moles is not given, so it is water. Molar mass is 18. So number of moles is mass upon molar mass, that is 72 upon 18, that is 4. So number of moles is given. Delta H is, we need to calculate. So delta H is equal to 4 into Cp is 75 joule per Kelvin per mole, and sorry, and this is mole. Delta T is 50 here. So mole will cancel, this is less in Kelvin, so this will cancel out. So 75 into 50 joule. So just multiply it. Okay, 4 into 75 into 50. This is not correct. This is 15,000 joule, that is equal to 15 kilojoule. But I think I have some problem in this value. I'll check this. Well, I will check this, and in the next class I will tell this. So this would be the answer actually. Let's see in the next class. I think I have changed some values here. I'll see the assignment and then tell this value, whatever the problem is. To 80 at constant pressure. So Cpm is given. Everything is fine, I guess. Here. Delta H is in kilojoule. So this is joule per Kelvin per mole, and this is mole. So mole cancel out. Joule per Kelvin into delta T. Delta T is 30 degrees to 80 degrees. That is 50 degrees. I'll see this and we'll get back in the, I think there is some problem in these options, I guess. Let's see this and I'll confirm with sir, and then in the next class I will tell this. For the combustion of 1 mole of liquid benzene at 25 degrees Celsius, the heat of reaction at constant pressure is given by this. Heat of the reaction is given. What would be the heat of reaction at constant volume? Okay, heat of the reaction at constant volume, that is delta U. We need to calculate, and delta H is given. Delta H is given delta U we need to calculate. So we know that delta H is equals to delta U plus delta Ng RT, where delta Ng is change in number of mole of gas in the reaction. So delta Ng is equals to, in the product side number of moles are 6, and in the reactant side number of moles of gas are only gas. So delta Ng is the change in number of moles of gas in the reaction. So this is 6 minus 7 by 2, that is 12 minus 7 by 2, that is 5 by 2. So delta Ng is equals to 2.5. So delta H is given, that is 780,980 calorie, and delta U is need to be calculated, and delta Ng 2.5, or if you take it in calorie, it is 2, near to 2, 1.98, and temperature is 25 degrees Celsius, that is 298 Kelvin. So delta U is equals to minus 78098 minus 2.5 into 2 into 298 calorie. So just I will calculate it quickly. 5 into 298, 780,980. So this is giving minus 782,470 calorie. That is okay. I made any mistake. Okay, it was my let me check this. So it looks fine to me. I made some mistake somewhere. I think balancing is not correct for this reaction. Let me check this. So this is O2 7 by 2 O2, okay, that is 7 no. And this side these are 12 and 3 15. Okay, this is not correct actually. This is not balanced reaction. This is 7 by 2 O2 of gas, so this is and this side there are 7 O, and this side there are 12 O plus 3 15 O. So this is not balanced. So it should be 3 and 12. This is 12 3 15. Okay, so 15 by 2. This is 15 by 2. So this is 15 by 2. I'll check in the assignment also. Let me check the assignment first. I think there is this mistake in this assignment. I will confirm with the sir if there are any problems in this assignment, and I will just put the okay. This is not giving correct, so I'll confirm with sir. This is not a balanced reaction. Okay, so this should be 15 by 2 here. So this is 15 by 2. Then this is the balanced reaction now. Okay, now let's do it for 15 by 2. So delta Ng is 6 minus 15 by 2, that is 12 minus 15 by 2, that is 3 by 2, 1.5 minus. And delta H is equal to delta U plus delta Ng RT. Delta U will be delta H minus delta Ng RT, that is equals to minus 780,980 minus 1.5 minus of minus 1.5 R in 2 and T 298. So now calculate this. This is 894 plus 894. This is 780,980. This is 780 minus of 780, 086 calorie. So we can write it 780.086 kilocalorie. 780 kilo minus of 780 kilocalorie. So option A is correct. Question number 7. When 229 joule of energy is supplied to 3 mole of a gas at constant pressure. Okay. Number of moles are given, a constant pressure. The temperature of gas increased by this. So delta T is given. This is similar question that we have in assignment. So delta T is given, number of mole is given, and heat is given. Delta H is 229J. We need to calculate Cp and Cv. This at constant pressure heat is given, that is Qp, which is equal to delta H. We know this. Okay. So delta H is equal to N Cp delta T. So from here we can calculate Cp. Cp is delta H upon N delta T. So delta H is 229 joule, N is 3, delta T is 2.55. Okay. So this is, just calculate it quickly. 229 divided by 3 divided by 2.55, this is 29.9 joule per Kelvin per mole. We know that Cp minus Cv is equals to R. This implies Cv is Cp minus R, and R is 8.314 joule per Kelvin per mole, and this is 29.9. So 29.9 minus 8.314, this is 21.586 joule per Kelvin per mole. So we get the value of Cp, which is 29.9 joule per Kelvin per mole, and Cv 21.586 joule per Kelvin per mole. This is the answer. Okay. Now we move to the next question. Question number 8. After this, I'll take a short 2-minute break. After that, we'll start again. So question number 8. 1 mole of an ideal gas Cp is given, expanded reversibly and adiabatically. From 1 decimeter cube to 10 decimeter cube. And the initial temperature is 750 K Kelvin. The final temperature we need to calculate. So we have discussed in the starting that T v to the power gamma minus 1 is constant for adiabatic, reversible expansion process. So we can just simply put the values in this formula and get the answer. Like T1 V1 to the power gamma minus 1 is equals to T2 V to the power gamma minus 1. Now Cp is given. Okay, we need this gamma actually, and Cp is given. We know this gamma is Cp by Cv. So Cp is given, Cv is not. So we need to calculate Cv. Cp minus Cv is equal to R for 1 mole. Okay, for 1 mole Cp minus Cv is equal to R, and Cp 29.234 minus R is equals to Cv. Cv will be Cp minus R. R is 8.314. So this is 29.234 minus 8.314. This is 20.92 joule per Kelvin per mole. Putting the value here, Cp 29.234 divided by 20.92 Cp by Cv, 29.234 divided by 20.92. This is giving value 1.4. This is 1.4. So now we have gamma as well. And what else is given? Temperature T1 is given 750 Kelvin. T2 is need to be calculated. Volume V1 is given 1 decimeter cube. V2 is given 10 decimeter cube. So by putting the values, we can simply get the answer. Okay, now T1 V1 to the power gamma minus 1 is equal to T2 V to the power gamma minus 1. Just put the values now. So this is T1 is 750. Okay, let's take T2 is one side. T2 is equals to V1. T2 is T1 into V1 by V to the power gamma minus 1. That is equals to T1 is 750 into V1 is 1 and V2 is 10. Gamma is 1.4 minus 1. 750 into 1 over 10 to the power 0.4. So this is T2. I'll just calculate it quickly. 0.1 to the power 0.4. 0.1 to the power 0.4 is 0.4 actually. This is given 0.398. That is 750 into 0.398. So it is given 298.58 Kelvin. So the nearest option is 300 Kelvin. So this is the answer, 300 Kelvin. Since we have taken some assumption, so this is correct only. Okay, I'll start in 2 minutes again after the break. Okay, we will start again. The question is saying that the relationship between volume change in isothermal process and adiabatic process. Okay, there is this bracket and this bracket. Okay, for a pressure change from P1 to P2 is. Okay, they are saying that pressure is changing from P1 to P2. And for isothermal, this is the change in volume is delta Vi, and for adiabatic it is delta Va. The relation of volume of so we need to calculate this. Since we know that for adiabatic process PV to the power gamma is constant, and for isothermal PV is equals to constant. So let's start this. Let's say P I V, let's say this is ISO, is equals to P F V F. Sorry, initial will not be ISO. Let's say we are saying that this is ISO. Change new volume, and for this will be Pi Vi to the power gamma. If we take same initial condition, then Pf V Adia to the power gamma is these are the two equations. So from this equation, Pi by Pf is equals to V ISO by Vi, and from here V Adia by Vi to the power gamma is equals to Pi by Pf. So we can substitute this value here. So we will get V Adia divided by Vi to the power gamma is equals to V ISO divided by Vi. Now taking the log gamma log V Adia divided by Vi is equals to V ISO log of V ISO divided by Vi. So now gamma this we know that if we are taking expansion, then V final will be greater than Vi, so this is greater than 1. So this is greater than 1, so logo greater than 1, then this will be greater than 0. Similarly for this will be greater than 0, and we know that this is greater than 1. So this whole quantity, this side quantity V then this V ISO by Vi should be greater than V Adia by Vi. So this means that V ISO should be greater than Vi Adia. That means isothermal volume is greater than adiabatic volume. So V ISO is greater than Vi. So option 1 is correct. Now the next question, for an ideal gas following adiabatic reversible expansion, plot a log P versus log V. Plot of log P versus log V is linear with a slope equal to, okay, they are asking about the slope of log P versus log V, and we know that PV to the power gamma is equal to constant. Let's say C. So log of P plus gamma log of V is equal to log of C. Log of P is equal to minus gamma log of V plus log C. If we plot log of V and log of P, then log C will be the intercept and minus gamma will be the slope. Answer is minus gamma. This is according to y is equal to mx plus cm is slope, c is intercept. So this is intercept and this is the slope for log P versus log V gamma. Now to the next question. phase diagram is given, and this is a two-dimensional plot. The number of degree of freedom at point P1, P2 and P3, this point and this point, we need to calculate the number of degree of freedom. So we know that for such kind of phase diagram, we have restricted 1 degree of freedom, that is one, like if we are taking pressure and temperature, we are fixing volume, let's say. So 1 degree of freedom we are fixing, then there are 2 remaining. So while working on this, if we are not working on these lines, then the degree of freedom will be 2. And this is the triple point, so here the degree of freedom is 0, and on this anywhere on this line the degree of freedom is 1. So the answer is 2 at point 1 and 1 at point 2 and 0 at point 3. This is a 2 component phase diagram. Okay, so we can also do it with this. This degree of freedom formula, that is F is equal to C minus P plus 2, and since we have restricted one degree of freedom, so this is F minus P plus 1 reduced degree of freedom, F is equal to this. So there are this is 2 component system, so this is 2 minus P plus 1, that is equal to 3 minus P. So here the phase is, there is only one phase in this region, so this is 3 minus 1, that is equal to 2. In this region there can be three phases, like phase 1, this is phase 1, phase 2 and phase 3. There can be 3 phases, so this is 3 minus 3, that is equal to 0 for point 3, and point 2, here there are 2 phases, phase 2 and phase 3. So there are 2 phases, then this is equal to 3 minus 2, that is equal to 1. So 2, 1 and 0, this is the answer. Next question. Calculate delta S of 1 mole of an ideal monoatomic gas which is heated from 27 degrees Celsius to 227 degrees Celsius. Temperature 1 is 27 degrees Celsius, that is equal to 298 Kelvin. Sorry. Temperature 2 is equals to 227 degrees Celsius, that is equals to 498 Kelvin. 273 plus 227, that is equal to 498 Kelvin. Okay, so the 2 conditions are given at constant volume and at constant pressure. Temperature change is given, we need to calculate delta S. So we know that delta S at when temperature and volume are given, that is equal to NCV ln T2 by T1 plus nR ln V2 by V1, and if pressure is given, then it is ln T2 by T1 minus nR ln V2 by P1. So by putting the values in these formula, we can get the answer. At first part, at constant volume V1 is equal to V2. This implies ln V2 by V1 is equal to ln 1, implies which is equal to 0. So So this part will be 0. Similarly, in second part, P1 is equal to P2, ln P2 by P1 is equals to 1, like this is equals to ln 1, so ln 1 is 0, so this part is 0, so this part will remain for the both. So let's just erase the other part and solve this. Now this is part 1 and this is part 2. Part 1, this is n for 1 mole of gas, so n is 1, so delta S is equals to n is 1, delta S is equals to CV ln T2 is 498 Kelvin and T1 is 298. Now Cp and Cv for monatomic gas. For monatomic gas, Cp is equals to Cv is equals to 3 by 2 R. This implies Cp is equals to 5 by 2 R. So this is Cv. So this is 3 by 2 R ln 498 by 298. So just calculate this. R less it is 8.314. First calculate log. So this is 1.5 into 8.314 into 0.5135. This is equal to 6.4 joule per Kelvin per mole. Now second part, delta S is equal to Cp ln 498 by 298. This is equals to 5 by 2. R is 8.314 and this is given value 0.5135, same. So just solve this. 2.5 into 8.314 into 0.5135, this is giving 10.673 joule per Kelvin per mole. So this is 6.4 and this is 10.67. So the next question now. Calculate entropy change in evaporation of 1 mole of water at 100 degrees Celsius. Heat of vaporization of water is given. So it is very easy question. We need to calculate change in entropy, and we know that it is delta H of transition divided by temperature of transition. So this is transition, this is vaporization from liquid to gas. So delta S is positive. So delta H is given 2259.4 joule per gram. Okay. So this is delta H of transition. and temperature is given 100 degrees Celsius. Temperature is 373 Kelvin. Okay, so this is in joule per gram. You need to change it to joule per mole. So this is for 1 gram delta H, and this is for 1 mole of water. So for 1 gram it is 2259.4 joule, and since we know that 18 gram is 1 mole, so for 18 gram it will be 18 into 2259.4 joule. So this will be per mole. So this is per mole. So delta S will be 18 into 2259.4 divided by temperature of transition is 373. This is joule per Kelvin. Sorry, joule per mole. Joule per mole, and this is in Kelvin. So just solve this. (109.03). This is joule per Kelvin per mole. So now we move to the next question. The question is, calculate the entropy change accompanying the freezing of 1 mole of water at 25 degrees Celsius to ice at minus 10 degrees Celsius. Given the heat of fusion of ice at 0 degrees Celsius and heat capacity of ice and heat capacity of liquid water. Okay. Heat capacity of ice is 36.82 joule per Kelvin per mole. Heat capacity of water is 75.31 joule per Kelvin per mole, and this tells delta H of fusion is 6 kilojoule per mole. Temperature is changing from 25 degrees Celsius to minus 10 degrees Celsius. So we know that there is a phase transition in between. So first we have to go from 25 degrees Celsius to 0 degrees Celsius. This is water, liquid to liquid. Then there will be a phase transition at 0 degrees Celsius from liquid to solid, and then from 0 degrees Celsius to minus 10 degrees Celsius again solid to solid. So these are the processes that we are going through. So from 25 degrees Celsius to 0 degrees Celsius, this is delta S1 from 0 degree Celsius, this phase transition, this is delta S2, and from 0 degree Celsius to minus 10 degree Celsius, this is delta 3. So delta S is delta S1 plus delta S2 plus delta S3. Okay, so we will calculate differently and then put the value here and get the answer. So delta S1 is this is changing from 0 degree Celsius to 25 degree Celsius, that is temperature. If we consider temperature T 298 Kelvin first and T2 is 273 Kelvin. So delta S1 we have just calculated just written this formula at this. We know that we in the beginning we said that this change in volume is 0 for solid and liquid. So this is, we are going from liquid to liquid, and we know that the change in volume is 0. There is not any change in volume. So the formula NCV ln T2 by T1 plus NR ln V2 by V1, and V2 by V1 is equal to 1. So this is 0. So this reduced to NCV ln T2 by T1. So number of mole is 1 given. So CV of water is required here. So this is 75.31 joule per Kelvin per mole. Ln of T2 by T1. So just calculate it quickly. (273) divided by 298, and the log, this is giving minus 0.0876 and multiply with 75.31. So this is 6.598, or you can say 6.6, minus of 6.6 joule per Kelvin per mole. This is minus, we know that temperature is decreasing, so this is minus. So delta S1 is, delta S2 is phase transition from liquid to solid, and from going liquid to solid this will be negative. Since from going liquid to solid delta H should be negative, that is given 6 kilojoule, that is 6000 joule per mole. Temperature is temperature of transition is 273 Kelvin. Divide with 6000 by 273, 21.98 joule per Kelvin per mole. This is delta S2, this is delta S1. Now delta S3 is, again the same formula we can apply. This NCV, CV for ice, CV for ice ln T2 by T1, that is CV ice is given 36.82. This ln T2 is minus 10, that is 263, and T1 is 273. 263 divided by 273, and the log multiply with 36.82. This is 1.37 joule per Kelvin per mole. Okay. Now put these values in this formula. So delta S is equal to delta S1 minus 6.6 and delta S2 is again minus, this is 21.98 and this is 1.37. So the total is 23.95 joule per Kelvin per mole. Okay, so this is the answer. Now the next question is in partition function of one dimensional oscillator having equispaced energy level, one dimensional oscillator with equispaced energy level with spacing is kBt. The zero ground state energy is, you know that harmonic oscillator is having this, they are saying that this is zero ground state energy and then the spacing between all is kBt. Since we know that this is give q vibrational and we know, we just in the beginning I told that q vibrational, if 0 point energy E naught is equal to 0, then it is 1 over 1 minus e to the power minus theta by t, where theta is h nu by kb. So this is 1 over 1 minus, spacing is given kBt. So this should be equal to 1 over e to the power minus spacing divided by kBt. So this is kBt. So this will become 1 over 1 minus e to the power kBt divided by kBt. So this will cancel out. So this is 1 over 1 minus e to the power minus 1. This is equal to 1 over 1 minus 1 divided by e. So this is 1 over e minus 1 by e. This is equal to e divided by e minus 1. So q is e divided by e minus 1. Option C. Now the next question. Okay, we are having only two more questions. Translational partition function of H atom is this much. 8 into 10 to the power 33. And temperature is given 3700 Kelvin. Volume is 0.064 meter cube. What is the thermal wavelength? That is equal to lambda. So thermal wavelength, we know that Q translational is equal to 2 pi m kBt by h square to the power 3 by 2 into V, and we denote it by V by lambda cube, where lambda is equals to thermal wavelength and its value is h upon, this is cube, so h upon under root 2 pi m kBt is equals to lambda. Okay, so q translation. So this is the formula. Q translation is V upon lambda cube, and we need to calculate this lambda. Lambda is equals to V upon q translation to the power to the cube root. So V is given 0.064 meter cube. Q is given 8 into 10 to the power 33 under cube root. So this will give 2 to the power 3, and this is if we divide by 1 by 3, this is 1 over 2 into 10 to the power 11 cube root of 0.064. If we calculate this is 64 into 10 to the power 3 minus 3, sorry. So this is 64 into 10 to the power minus 3 to the power 1 by 3. So this is 4 to the power 3. So this is 4 into 10 to the power minus 1, that is equal to 0.4. So this is 0.4. So 0.4 divided by 2 into 10 to the power minus 11. This is 0.2 into 10 to the power minus 11. So lambda is coming 0.2 into 10 to the power minus 11. That is equal to 2 into 10 to the power minus 12. So this is the answer, 2 into 10 to the power minus 12. This is the last question. 17th question. Assuming H2 and HD molecule having equal lengths. Okay. The ratio of rotation partition function of these molecule at temperature above 100 Kelvin is. So Q rotation we know is equal to kBT by sigma h Cv, where B is h upon 8 pi square IC, and we also denote it as T by sigma theta B. Sorry, sigma theta R. So theta R is characteristic rotational temperature. So we are giving H2 and HD. Okay. Ratio of rotation partition function. Length they are considering equal. So we know that Q is inversely proportional to B and B is inversely proportional to I, so this will be proportional to moment of inertia I. Q is directly proportional to I. I is mu r square, so it is directly proportional to mu. So Q is directly proportional to mu. So Q of H2 divided by Q of HD is equals to mu of H2 divided by mu of HD, that is equals to 1 into 1 divided by 1 plus 1 divided by 2 into 1 divided by 1 plus 2, 1 into 2 divided by 1 plus 2. So this is 1 over 2 and this is 3 over 2. One over 2 divided by 3 by 2, that is equal to 2 by 3. That is equal to 1 by 3. Mistake, I guess. Mu of H2 is half and mu of HD is 2 by 3. Half divided by 2 by 3. So this is half into 3 by 2, this is 3 by 4. This is the answer, 3 by 4. So that's it. Thank you. I'll be here in the meeting for the next 10 minutes, and if someone joins or someone have any problem, I'll be here only. Thank you. Okay, thank you. I am leaving the meeting now.